Okay, so now we're going to prove that a pair of congruent triangles gives us an isometry that maps one triangle to the other one. So let's suppose I have triangle ABC and DEF, and I suppose they're congruent. Then what I claim is that there exists an isometry T, so that T sends the triangle ABC onto the triangle DEF. And so T of A is D, T of B is E, and T of C is F. And then in our proof, we're going to construct this isometry pretty much explicitly. And in the process, we will see that our isometry then allows us to have this written as a composition of 0, 1, 2, or 3 reflections. Most of the time, people word this as 2 or 3 reflections. I'll have you think about why it is that 0 or 1 can always be inflated to give you 2 or 3. Okay, and then I told you there exists an isometry. We're going to construct it explicitly, but this isometry is unique, and that uniqueness follows from the theorem that we just proved, that if you know what an isometry does on a triangle, it is globally determined. Okay, so the key idea of the argument is to use something we discussed in our Zoom meeting last week, which is a great way to send a point P to a point Q. Actually, it's the only way of doing it with a reflection. But a great way of moving P to Q is to reflect about the perpendicular bisector of the segment PQ. So we're going to use that over and over again. And the idea is we're going to systematically move the vertices of ABC onto the vertices of DEF, and we're going to do it through up to 3 reflections. We'll skip those that are not necessary, but the worst case scenario will be 3 reflections. Right, so the first step is we reflect through the perpendicular bisector of AD. That's going to send A to D, and then it's going to move B and C to new points, whatever they are. And so I'm going to call them B prime, C prime is the result of that first reflection. Then, in a second go, right now we have a new triangle, triangle D, B prime, C. We now want to move B prime onto E. So then we're going to reflect through the perpendicular bisector of B prime E. We're going to check this doesn't actually move D. So that's where this pointwise characterization comes back into play. And then we're going to get a new triangle that I'm going to call DEC double prime. Right, C prime moves, and that gives us a point C double prime. If C double prime is F, we're done. Actually, also at previous steps, if our triangles were equal, we just stop. But if not, we can reflect through the perpendicular bisector of C double prime F, and then we're done. So in that last case, if we have to do all 3 of them, that takes us 3 reflections. If we do fewer, we have fewer reflections. Okay, so that's the sketch of the proof. Let's go ahead and work it out in detail. So step 1, if A is already equal to D, we skip the step and move on to step 2. Otherwise, we reflect across the perpendicular bisector of the segment AD. So we obtain 3 new points, A prime, B prime, C prime, but A prime is the same as D. Right? So the first thing we do is we draw the segment AD, and so I have it here in these little dots, and then we take the perpendicular bisector of that. So that gives me this red line here, this perpendicular bisector. And now we're going to reflect across that red line. And I reflected, and I get this triangle I have here in green. And this guy here is, D is the same as A prime. It's the image of A. And I have B prime and C prime, whatever they happen to be. Okay, step 2. We start with this arrangement. And now what we want to do is we want to reflect across the perpendicular bisector of B prime E. So I've put in here the segment B prime E in little light gray dots and the perpendicular bisector in red. So now the key thing is our point D, which is the same as the point as A prime, right? D is incident to this bisector because the distance from D to B prime is the same as the distance from A to B by the fact that we used an isometry. But the distance from D to E is also equal to that by our hypothesis that the triangle ABC was congruent to the triangle DEF. So that means that this point D, or A prime, is on that perpendicular bisector of EB prime, and hence it doesn't move when I take the reflection. Right, so I'm going to do that reflection like I just said, and I get the following picture. Right, so B prime moves to E, D stays where it was, and C double prime ends up down here. And I have this, now this blue triangle is the image of my green triangle under that reflection. Okay, and now we're left with one last go in this example. So if C double prime was actually equal to F, we'd do nothing at the set, we'd skip it. If not, we reflect about the perpendicular bisector of C double prime F. And the claim I make is the perpendicular bisector of C double prime F has to be the line through D and E. So I have the details here, but the basic idea is, again, we use the pointwise characterization of the perpendicular bisector, right? That all the points on that line DE are equidistant from C and from C double prime. And so here we have the details of that argument, and then from the pointwise characterization, that gives you that the line DE is the perpendicular bisector of C double prime, and this gives us the result. Okay, so let me quickly tell you about a corollary, and then I'll illustrate this construction with a little bit of GeoGebra stuff. Okay, so the corollary is if T is any isometry of the plane, then it can be written as the composition of either 2 or 3 reflections. So all you have to do is take any triangle, your favorite triangle, look at its image under T, then you can construct an isometry that takes triangle ABC to its image under T. We can decompose that as 0, 1, 2, or 3 reflections by our previous theorem. And then by the uniqueness, T is equal to this composition of 0, 1, 2, or 3 reflections. And I'll have you think about why 0 or 1 reflections are not very exciting cases, and we can bump it up to 2 or 3 basically by throwing in some bogus reflections. Let's illustrate the steps of our proof of this theorem that we can move one triangle onto the other using either 2 or 3 reflections. So here I have a triangle ABC, and by construction I've made it so that it is congruent to triangle D, E, and F. Okay, so I can play around with it. I get these 2 triangles. And the first step of the argument is we find the first 2 points that we want to smack one on top of the other. So here I have A and I have E. I have A and I have D that I want to smack on top of each other. So I want to send A to D. So I construct the segment AD, and I take the perpendicular bisector of that segment. And then now I'm going to use the reflection tool to reflect my triangle ABC across the line that was that perpendicular bisector. Right? So now I have a new triangle A prime, B prime, C prime, and I have made it so that A prime and D are the same point. Okay, so now we are going to construct the segment between the next 2 points that need to go to each other. So in this case, I want to send B prime onto E, and so I construct that segment B prime E, and I need my perpendicular bisector of that segment. And the key thing is this point that is both A prime and D is incident to that perpendicular bisector, so it doesn't actually move at all. Okay, so I'm going to reflect my triangle A prime, B prime, C prime about the perpendicular bisector I just constructed, and boom, I have now landed directly on top of the triangle DEF. So in this example, we used 2 reflections in order to send my original triangle ABC onto DEF, right? DEF here. So that illustrates the proof in this case where we had 2 reflections necessary. Okay, so now let's do this again. In this example, I've arranged it so we need 3 reflections. So here I have ABC, it's congruent to DEF, and we're going to proceed the same way. And I construct the segment AD because I want to send A onto D. And I now construct the perpendicular bisector of that segment, and I reflect across that line. Right, so I send this guy up there. Oh, GeoGebra named my points a little bit funny. It's A1 prime, B1 prime, C1 prime. Okay, and now I construct the segment I want to send B to E. Right, so I construct that segment right there. So that's the segment from B prime to E. And I construct its perpendicular bisector. And I reflect across that perpendicular bisector. And now I have this new triangle here. Okay, GeoGebra has named it G1, H, and I. I want to send this I to F now. So I construct the segment here, IF, and I construct my perpendicular bisector of that segment. You notice both these points are on the perpendicular bisector because they are equidistant from the endpoints, right? So that means that they don't move when I do the reflection. So I take my triangle, and I reflect it about my perpendicular bisector, and now I've landed on top of DEF as desired. So in this example illustrates the situation when we needed to do 3 reflections. Thank you for watching, happy mathing, and see you on the next one.